Hello everybody. In today's video, we're going to talk about the kinetic energy theorem, or kinetic energy and the work energy theorem. But what is the work energy theorem? To put it simply, it describes how work done on an object affects its velocity. This directly connects it to kinetic energy. Let's break it down. Now, based on these three objects down here that I have drawn, it shows that when a force is applied in the direction of the direction's motion, the object speeds up, as we can know that the force is the direction that it's accelerating. And when the object, this means that the work is positive, as it's displacing in that direction. Conversely, when the work is applied opposite in direction to the direction of motion, the object slows down. We know this the because this if it's accelerating in a different way than its velocity is, it eventually slows down. And we know that this work is negative. And going back to the last example, we know that the force on an object which is perpendicular that means the work must be zero. As we remember, work equals F times displacement cosine of zero, or cosine of 90, since the angle between the displacement and the force is 90, which gives us zero. Alright, when a force is applied, okay, now we're gonna talk, good, we're gonna talk about how are we gonna derive the equation for the work energy theorem. So let's start a little with a diagram here, so we can get an idea of how we're going to derive this equation. So we'll start with a box that's going to slide from point x1 to x2 over this displacement x. We'll have all these variables here will be known. So velocity 1, the initial velocity, is known. Second velocity 2 is known. Mass is known. Displacement is known. And then we have this known force, which is pushing the object in the direction of displacement, which means work is positive in the example. We're going to go back to our kinematics equation. V squared, which is V final, equals n V naught, which is going to be V1 squared, plus 2 times acceleration times s, which we're replacing the change of x with our symbol s, which represents displacement in our example here. And so we know all those variables except for acceleration, and we can get our acceleration by using our free body diagram to get an idea. This one's pretty simple. The sum of the forces just equals the force. But we know that the object is accelerating, so the sum of the forces also equals mass times acceleration, and then equals to what the sum of the forces are. And as we can see, the only unknown is acceleration. So going back to our kinematics equation, if we can factor out our acceleration, we can eliminate this unknown variable and also eliminate having to calculate or know acceleration. So we factored it out, and now we need to plug it into on the right equation that we used from a free body diagram. And as you can see, we're going to multiply the denominator, which is the 2s, on both sides so we can get our equation force times displacement, which will get our work in this example. And once we separate those, we can distribute our mass variable to the initial velocity times the final velocity. But if you remembered, going back, we'll just draw the work equals the force times displacement, and kinetic energy is equal to 1 over 2 mass times velocity squared. So these are the key equations to drive this work energy theorem, because once we get our displacement over on the right side, we can replace it with work. And we can see that once we distribute our mass, we will get 1 over 2 mass times final kinetic energy minus 1 over 2 mass times initial velocity squared, which brings us back to kinetic energy or work energy theorem. And we just have to replace those. But if you also notice, one of the rules for using kinematics from earlier in our physics class, force had to be like consistent. It couldn't change piecewise, and this means that force has to be constant in our example. So that does bring up the question, then how do you solve it when you have a varying force? This means we have to use our calculus problems that we solved in calculus, where you have to integrate over this variable force times the derivative of the displacement, which I'll draw here in a second. And also note, yes, my audio wasn't working when I recorded this, so this is an talk over of, of my 20-minute video. So I'm spending 40 minutes talking here, pretty much. Alright, which brings us to where I'm talking about the relationship between those. But now that we now that we have a good idea between the relationship between kinetic energy and work, we can start solving our some problems to where we can apply this idea. All right. So in our example, we're gonna have a 200 kilogram steel hammerhead, which is attached to a column, or like a shaft, which brings it down as meant, and then it's gonna be lifted up 3 meters above this I-shaped pillar. And because we know that it's lifted up to a certain point and dropped, the velocity must be 0. And we'll have our I-shaped column right below it. The problem goes into asking or telling us that when the hammerhead comes down and hits the I-beam, it drives the beam 7.4 centimeters deeper into the ground. And then just as the hammerhead hits the pillar, it exerts a 60 Newton friction force back up at the hammerhead. And when we go to question A, it asks us this. It tells us what is the speed. Use the work energy theorem to find the speed of the hammerhead just before it hits the I-beam. So those are our 3 cases. We have when the hammerhead's pushed up or lifted up 3 meters just before it hits just as it hits the I-beam, and well, it still has its velocity, and then when it finally comes to a halt, driving the I-beam 7.4 centimeters into the ground. And because we're working with our work energy theorem, where work equals force times displacement, we know that we're gonna have to find our forces here. So it's always a good idea to start drawing our free body diagrams like as we go, so we can get an idea of what forces are acting on our object throughout the scenario. So in our second example, we have this friction force, which is pushing the hammerhead back up, but also the greater force of gravity pushing down. And then our question is, what is the velocity just as it hits the hammerhead? So we're going to start with drawing our work energy theorem equation that we derived from the previous slide to solve this problem here. So we have work equals K kinetic energy final minus kinetic energy initial. But as we remembered, kinetic energy is equal to 1 over 2 mass times velocity squared. So when that velocity is 0, this means that the kinetic energy is also 0. So that eliminates us having to solving the initial kinetic energy. And work is also equal to force times displacement. And looking back at the variables, we know that force, the net force, is going to be killer. It's going to be the weight of the hammerhead minus the friction, which we know the friction, we know the mass, we know g. So those are our knowns for the force times our displacement, which we know our displacement, which is 3.0 meters, equals the kinetic energy final, which is 1 over 2 times our mass that we know, times the final velocity just as it hits the I-beam, which is what we're looking for. So this leaves us with just a single variable, or velocity, which means we can solve for it now. So we get velocity on its own, and we set it equal to ma- ma- mass times g minus our friction force times displacement over 1 over 2 the mass for a previous problem. And I'll calculate this problem so we can get it, so I can show you what the velocity should be. Alright, so velocity equals 7.55 meters over seconds. So this solves our question, what is the velocity as the object hits the I-beam in the question? And the next question for our problem, what is the average force the hammerhead exerts on the I-beam, ignoring the effects of air resistance? So we know that when this hammerhead hits down into a rest, we know that the normal force is what's going to be equal to this force we're looking for. But before we go to there, we'll going back to check our units. So we know that joules over kilograms gives us mass squared over second squared, and the square root of that is mass over seconds. That's a really good way. Checking your units is a really good way to make sure that you at least use the right formulas. It's also a good idea to check what the numbers you started with. I have a issue where sometimes the values that I use to put into my equations aren't the values that are listed on the exam prompt, because I just my brain when I was writing it just fits in a number as I'm going. So always make sure you don't do that. And then we're going to draw our third case, which is where the I-beam is pressed down 7.4 centimeters into the ground. And we know that the iron head stops at this moment, so the final velocity is equal to 0. And let's go back to the work energy theorem. We use the work equals the final kinetic energy of 3, and then the kinetic energy case 2. So we're going to set the work equal to force times displacement. We know the displacement, which is 7.4 centimeters. And let's draw our free body diagram so we can know what all the net force, which is acting on this object. So we have the normal force, which is pushing back up. That's what we're looking for. We have the gravity, which is the weight pulling down. And then we have our friction force of the I-beam, which is from the impact. We know that the final kinetic energy is equal to 0 as the velocity is equal to 0, which just leaves us with K2, or kinetic energy case 2. And we'll substitute the forces. If you notice that we're placing the gravity first, which should be negative, which will reverse the signs. Because if you remembered, the force that you push into the object, the normal force is the equal but opposite. And as we solve this problem, we find that a lot of the variables from the provided information, we know how to solve this. So now we separate the normal force from the equation, so we can find how much the hammerhead pushed into the hit with how much did the hammerhead do. And so we have our normal force all by itself, and we're going to plug in the values and solve for it here. Alright, now we're going to plug in the variables. So we know that mass equals 200 kilograms. My bad, I wrote newtons there. Times g, which is 9.8 meters over second squared. We'll fix the units right here, write kilograms. And then we'll write the units for g. Minus 60 newtons of the friction force pushing back up. Plus 1/2 times the mass of the hammerhead, which is 200 kilograms, times the initial velocity in this case too, which we found from our previous problem, and this will be over the displacement of 0.074 meters. And now we'll solve for the normal force. Alright, and we know that newtons equals 78,000 newtons. Alright, that is all. We've seen that work and kinetic energy are closely related, and by using the work energy theorem, we can analyze motion without needing to directly calculate acceleration or time. And thank you for watching my video today.